Good morning. Again, I am in front of you to teach you the next part of design of RC structures. The name of subject is Design of Concrete Structure 2. The name of subject is Design of Concrete Structures 2. So what exactly we have done in design of concrete structure 1 and what exactly we have to do in design of concrete structure 2. So in previous semester mostly we have completed the design of RC elements, design of beam for shear and bending. That part is already completed in last semester. Design of slab for bending and shear, design of a column for axial compression and design of a footing. All these RC elements design procedure is completed. Now we have to consider some special forces on beam. Again, there are some other special RC elements we have to study in this subject. Now, what is exactly the syllabus of this subject? I will tell you one by one. Again, we have to use the IS 456 2000 version. We have to use IS 456 2000 version for design of a RC element in this subject also. Now, what is the syllabus? So I will tell you one by one. So in section 1, in that unit 1, so you have to consider the special force on beam, that is a torsion. That means already we have designed the beam for shear and bending, but in this unit you have to consider one special force, that is a torsion. Exactly the way the torsion is developed practically, that part I will cover in this unit. So what is the content? Design of beam for torsion. Design of beam for torsion. This part we are going to cover in this unit. Again, there is a combined effect of, we have to consider the combined effect of bending moment, okay, shear force and torsional moment. So again we have to consider the combined effect of bending moment, shear force and torsion moment in this unit. The simple, we have to design the beam for torsion. What are the steps? As per the IS 456 2000 consideration, that part we have to cover in this unit. Now, what is the content of unit number 2? What is the content of unit number 2? So, in unit number 2, again, you have to design the beam, but beam is continuous. That means design of beam, design of continuous beam, design of continuous beam, that part is covered in this unit. We know that when the beam is simply supported, it is treated as a determinate structure. But when beam is continuous, so the structure becomes indeterminate. That means some extra forces are developed in that structure, and that forces you have to first analyze and then design. Okay, so practical point of view, the all beams are generally continuous beam. Rare case there is a simply supported beam. So this unit covers the design of a continuous beam. In that you have to consider the analysis of continuous beam, okay, that means you have to do first analysis and then design. Analysis of continuous beam using exact and coefficient method, that I will tell you detail when we are going to detail in unit number 2. Okay, analysis of a continuous beam, redistribution of a moment, moments, that part I will tell you later on. Okay, what exactly the redistribution of a moment? These are the contents of unit number 1 and unit number 2. Now, what is the content of unit number 3? What exactly we have to do in unit number 3? So it is design of a water tank. So it is the design of water tanks. Design of water tanks. So, but you have to remember here, design of a water tank is related to the working stress method. So you have to consider the working stress method. Only for this unit you have to use the working stress method. Other all units are related to limit state method. That you have to remember. Why? I will tell you later on exactly why we are going to use working stress method for design of a water tank. I will tell you later on exactly. Then in design of water tank, in that introduction of working stress method, that is the sub part of this unit. Then design of circular water tank, design of circular water tank resting on ground, that part is included in this unit. Design of a circular water tank using different methods, okay, and rectangular water tank and rectangular water tank. So this is the some important list out part of the unit number 3 in that design of a water tank. But remember that you have to use the working stress method, introduction of working stress method, design of a circular water tank, but it is only resting on ground, and design of a rectangular water tank. This is the contents of section 1. So again I am going to repeat. Section 1 contains unit number 1, design of a beam for the torsion. That means already we have designed the beam for the bending and shear. Now you have to consider one special moment, it is a torsion, and you have to consider the design steps when the beam is subjected to torsion. IS 456-2001 you have to strictly use. Unit number 2, design of a continuous beam. When there is a continuity, the beam become indeterminate. So due to indeterminacy of the structure, there are development of some extra moments. That moments you have to consider, and design of continuous beam you have to do. For that you have to use analysis first, analysis of a continuous beam using exact method, and you have to use here exact method. You have to use here exact method and coefficient method, or it is called a I-scored method or coefficient method, I-scored method. Okay. For analysis purpose, you have to use two methods. One is the exact method and another one is the I-squared method. Exact method already we studied in theory of structures. That means moment distribution method, three-moment theorem method, matrix method, and slope deflection method. These are the exact method. And I-squared method means one simple coefficient method is given in I-squared, I-squared 5, 6. That method you have to use for the analysis purpose, and then you have to design the continuous beam. Okay. Now redistribution of moment, I will tell you details about this concept later on. And finally, unit number 3 is the design of a water tank, but you have to use the working stress method. Introduction of working stress method, then design of circular water tank only resting on ground, elevated part skipped from this unit, and rectangular water tank you have to do. So this is related to section 1. This is related to section 1. Okay. So now what about the section 2? Now what about the section 2? So this is the section 1. So this is the section 1. Now I will tell you exactly what about the section 2. What about the section 2? The section 2 is not related to the RCC structures. It is related to the pre-stressed concrete structures. Okay. So section 2 is related to the pre-stressed concrete. Section 2 is related to pre-stressed concrete. That means you have to study the pre-stressed concrete in this total section. Okay. Now again, what are the contents? Now the unit number 4 is related to the introduction. Related to the introduction of pre-stressed concrete. Introduction of pre-stressed concrete that you have to consider in this part. Then pre-stressing systems. What are the pre-stressing systems that you have to study in this unit? How the pre-stressing is done, all these things I will tell you later on. Pre-stressing systems. Okay. Then analysis. Then analysis of pre-stress. Analysis of pre-stress beam. That means you have to find out the stresses due to pre-stressing force in this point. It is analysis of pre-stress beams. In that you have to use the three concepts. In that you have to use three concepts. One is a stress concept. Okay. Second is a strain concept. Strain concept also called it is a C-line concept. Okay. And finally, you have to use the load balancing concept. Load balancing concept. Okay. So these three concepts you have to use for analysis of the pre-stress. So this is the some short contents of the unit number 4. Now, what is about unit number 5? Now, what is about unit number 5? Unit number 5 is related to the loss of pre-stress. Loss of pre-stress. Okay, unit number 5 is related to loss of pre-stress. That means you have to find out the losses. Okay, and count it. And finally decide that how much loss is there. This is the one simple unit, loss of stress. So you have to count all the losses, friction loss, anchorage slip loss, shrinkage loss, creep loss, all these 6 to 7 losses are there. You have to find out, list out, and finally decide that how much loss is developed in pre-stressing force. That I will tell you exactly when we are going to study this unit. Now finally the unit number 6. Finally unit number 6. Unit number 6 contains the design of pre-stress beams. Design of pre-stress beams. So these are the somewhat brief introduction of unit section 2. In section 2, is totally related to the pre-stressing component. Let's start the design of beam for torsion. It is the unit number 1. Design of beam for the torsion. Using, you have to use IS 456 2000 version. Use IS 456 2000 version. Basically, design of beam for the bending and shear, that part already we have covered in last semester. Now we are going to design the beam for torsion. Now what is the design of beam? Design of beam means you have to decide the dimension of beam, you have to find out the longitudinal reinforcement, you have to find out the shear reinforcement, that's it. Now what exactly the torsional moment effects on beam? So what is the effect of torsional moment on beam? When torsional moment is developed on beam, it increases the shear force and bending moment. The amount of shear force, the amount of bending moment increases due to effect of torsional moment. And that increased amount you have to consider for design purpose. Now, I am going to tell you exactly at which location the torsional moment is developed at practical point of view. At practical point of view. When there is a beam with a cantilever slab, when there is a beam with cantilever slab, so this is a cantilever slab, this is a beam, so let's consider the axis of beam, okay, it's vertical axis, horizontal axis. When slab is attached to the beam, as per practical point of view, it is treated as a chhajja above the window level. In this situation, the torsional moment is developed on beam like this. In this situation, the torsional moment developed like this. Torsional moment developed like this throughout the section of beam. Throughout the section of beam. Let's consider the simply supported beam. So this is the simply supported beam, and due to the connectivity of cantilever slab, the torsional moment is developed like this throughout the span. So this is the first situation where the torsional moment developed in practice. Second thing is when suppose this is one of a simply supported beam and one beam is exactly rest on this beam at this location. Get it? So this is one of a simply supported beam. On that beam, when another beam is going to rest, at that situation, the torsional moment is developed. At that situation, the torsional moment is developed. Look here, in this situation, for the third section, throughout the length, throughout the span, the torsional moment is uniformly distributed. Okay? Okay? So you have to design the lintel section, you have to design the third section for the torsional moment. Okay? Second thing, in next situation, when one beam is going to rest on another beam, at that particular location, the torsional moment is developed. Okay. Third thing, next is the third thing is when beam curved in plan, when beam is curved in plan, when beam is curved in plan, when beam is curved in plan, in this situation, the torsional moment is developed on the beam. That means when beam is curved in plan, so let's consider this is a beam, okay, and it is curved in plan. It is curved in plan like this. Okay, so this is the 3D view. When beam is curved in plan, having a curvature in plan, so in this situation, the torsional moment is developed on the beam. Okay, so these are the some practical situations where the torsional moment is developed. Simply we know that moment is equal to force into perpendicular distance. We can find out easily the torsional moment on site. The beam curved in plan is mainly related to the water tanks. Mainly the water tanks having the beam which are curved in plan. In such situation, you have to consider the torsional moment. Next is, what is the effect of torsional moment on beam? What is the effect of torsional moment on beam? That part I am going to tell you now. Already I have told you the torsional, due to the effect of torsional moment, there is a development of extra shear force and there is development of extra bending moment. That extra shear force and that extra bending moment you have to consider and finally design the beam. Okay. Same thing, whatever you have followed in last semester for design purpose, that same thing you have to do here, but you have to consider the extra amount of a shear force and extra amount of a bending moment due to effect of a torsional moment. Okay. Now as per the IS 456, clause number 41.3, clause number 41.3, so this clause is related to the design of beam for shear and torsion. Design of beam for the shear and torsion. That means it is a combined effect of shear and torsion. What exactly you have to do, and for the design purpose, with the reference of page number 75, you have to follow the steps and finally design the beam for the torsion. Get it? That means all steps are given in IS code all criteria are given in IS code related to the torsion. The clause is 41.3. The heading of the clause is shear and torsion. Refer the page number 75, IS 456-2000 version. Step by steps. Step number 1, step number 2, step number 3, step number 4. Like this, all steps are given in IS code. You have to refer these steps and design the beam for the torsion. Okay. Now already I have told you the extra amount of a shear force and extra amount of a bending moment is developed in the beam due to the effect of torsion, and that extra amount of a shear force, extra amount of a bending moment is called equivalent shear force and equivalent bending moment. First you have to find out the equivalent shear force. First you have to find out the bending moment, equivalent bending moment. You have to refer both the values and finally design the beam for the bending and shear. Design the beam for bending means what? Design a beam for bending means you have to provide the sufficient depth for that bending moment, and you have to provide the longitudinal reinforcement for that bending. Again, what is the design of a beam for shear? You have to design the shear reinforcement. That means in form of stirrups or bent up bar like this. We have already done this in last semester for design of a beam for the shear. Same thing, same steps you have to follow and do the design of beam for torsion. Now I will tell you exactly how the steps are going on. Okay. So step number 1. What you have to do? Step number 1. The step number 1 is related to equivalent shear force. Okay. Equivalent. Equivalent shear force, and symbolically it is called VE. V is symbol generally used for the shear and E for equivalent. Equivalent shear force means VE is equal to this formula is directly given in IS code on page number 75. Refer the page number 75. I have IS code. Refer the page number 75. On this, the equivalent shear force VE's formula is directly given. What is the formula? VE is equal to VU plus 1.6 TU upon B. So this is the formula. Okay. So this formula is applicable for calculation of equivalent shear force on beam. So what is the VE? VE is the equivalent shear force. What is the VU? VU is the shear force developed due to the normal effect without torsional moment. Okay, and this is the amount of extra shear force. This is the amount of extra shear force developed due to the effect of a torsion. Developed due to the effect of torsion. That means if you add both these things, you get the equivalent shear force. You get the equivalent shear force. Now, what is the V? Already I told that it is the equivalent shear force. Now, what is the VU? VU is the ultimate shear force. VU is the ultimate shear force. VU is the ultimate shear force. That means the shear force developed due to the normal loading without consideration of a torsional moment. Okay. Now, what is the TU? TU is the ultimate. TU is the ultimate torsional moment. TU is the ultimate torsional moment. And what is the V? V is the width of the beam. B is the width of the beam. B is the width of the beam. For L and T beam, B is the width of the web. For L and T beam, suppose this is the rectangular section. Okay, so this is the width of the beam. Okay, and when we consider the slab, that means connected with the web like this. So this is a T section. In such situation, consider the B is equal to width of the web. Width of the web. Okay, so this is the web portion. So this is the web. Okay. So in calculation of torsional analysis, first you have to find out the equivalent shear force. And this formula is directly given in IS code on page number 75. On page number 75, you have to refer IS 456 2000 version. IS 456 2000 version. Bu is a normal ultimate shear force. 1.6 D upon B is the extra shear force developed due to the effect of a torsion. Okay, B is the width of the beam. Using this formula, you have to find out the equivalent shear force. You have to find out equivalent shear force. Now next what you have to do? You have to find out the equivalent shear stress. You have to find out the equivalent shear stress. That means whatever we have done in design of a shear reinforcement in last semester, same thing you have to do. You have to find out the equivalent shear stress. Equivalent shear stress. Equivalent shear stress. Okay, it is the tau VE. We know that the tau VE is equal to force divided by cross sectional area. Force divided by cross sectional area. Whatever we have followed the steps in shear reinforcement in previous semester, the same steps you have to follow. Equivalent shear force, then equivalent shear stress, VE divided by B into D. Stress is equal to force divided by area. So force is the equivalent shear force. B into D is the effective area you have to put here, and finally find out the equivalent shear stress. These are the two main first steps you have to consider. Okay? Got it? Equivalent shear force and equivalent shear stress. Now what is the next step? I am going to rub this now. Now, equivalent, step number 2 is the equivalent shear stress. Equivalent shear stress is a tau VE. So we know that the tau VE is equal to V divided by B into D. Now decide that whether the shear reinforcement is required or not as per our previous shear reinforcement steps, whatever we have followed in last semester for design of a shear reinforcement. Okay, that means then find out step number 3. Calculate permissible shear stress. Calculate permissible shear stress tau C. Permissible shear stress tau C with reference of IS 456, with the reference of IS 456 2000 version. Okay, for that you have to refer the page number 73. Okay, I will show you page number page number 73, table number 19. So with the reference of IS 456, page number 73, table 19, and find out the tau c. Okay, the tau c depends on the percentage of steel. Okay, so tau c depends on percentage of steel. It is PT. It is 100 AS upon beam T. 100 AS upon beam T. And find out the tau c using this table 19, page number 73 of IS 456. And again refer and again write down the value of tau c max from table 20, same page, and on page number 73. So now we have the three stresses. One is the tau VE, equivalent to shear stress, tau C, permissible shear stress in concrete, and finally tau C max. Now, as per our previous semester stats related to the shear, you have to compare these three stresses. That means the first comparison, already I have told that tau C max is the greater as compared to both these stresses. Always tau C max. If your tau VE is more than tau C, okay, please concentrate on this comparison. Tau C max is the greater maximum. Now the main comparison is between these two stresses. Tau VE is more than tau C. That means equivalent shear stress is more than permissible shear stress. In this situation, shear reinforcement is required. Shear reinforcement is required. That means shear reinforcement is required as well as longitudinal reinforcement is also required. In this comparison, shear reinforcement you have to design as well as longitudinal reinforcement is also you have to design in this comparison. Then again, if tau C max is more than tau C is more than tau V, now the tau C is more than tau V, the shear reinforcement is not required. Shear reinforcement is not required. But you have to design the minimum shear reinforcement. With the reference of page number 48, IS 456 2000. Okay, that point I will tell you later on while solving the problem. So, two comparisons. One is this, another is this. In this case, tau C max is more than tau V, more than tau C. Shear reinforcement is required. So, only shear reinforcement is required. You have to design the extra longitudinal reinforcement also. That means longitudinal and shear reinforcement you have to design by considering these comparisons. Second thing, if tau C max is more than tau C, then tau V, that means your permissible shear stress in concrete is more than tau VE. The shear reinforcement is not required, but you have to design the minimum shear reinforcement. With the reference IS 456 page number 48. Again, if your tau VE is more than tau C max, okay, if your tau VE is more than tau C max, so this is a very dangerous case. So you have to redesign the section. In this, redesign the section. Redesign the section or reduce the value of tau VE. Please concentrate. If tau VE is more than tau C max, it's very dangerous case. Any shear stress related to the RC element, it should not be more than the tau C max. But here, the equivalent shear stress is more than tau C max. So this is a dangerous case. So you have to redesign the section or reduce the value of a tau VE. So how to reduce the value of tau VE? We know that tau VE is equal to VE divided by B into T. V divided by B into T. Okay? If we reduce the value of VE, obviously this value is reduced. Okay? So what is the VE? What is VE? VE is equal to VU plus 1.6 TU upon B. 1.6 TU upon B. Okay? So when this value is less, then obviously this value is less. Okay? You can reduce this value by increasing the dimensions. Okay? That already we know that. But when you want to reduce the effect of torsion on beam, increase the width. Increase the width of the section. Increase the width of the beam. By increasing the width of the beam, obviously this value becomes less. Again, this value becomes less, and there is no redesign of a section. Okay? So this is the some explanation up to the step 3. That means first find out the tau VE. First we find out the VE.